the first thing we need to discuss is something called wave-particle duality. So it's the idea that things that we conventionally think of as waves in classical physics, they have particle aspect, particle behavior to them, and things that we think of as particles, they actually have a wave behavior to them. So that's respectively chapter 3 and 4. The first subject in your chapter 3 is black body radiation, and how Planck realized that electromagnetic waves cannot come with arbitrary energies, and energies have to be discretized or quantized, and that somehow solved some experimental observations that could not be explained before that. I don't think we should discuss it here for two reasons. First, in order to really explain how quantization resolves some experimental puzzles, it will take a lot of time, and it will also require some more knowledge than you currently have. You need to know a little bit about thermal physics, Boltzmann distributions, and things like this to explain, even qualitatively. I found from teaching this before that there's very little gain from doing that, and it mostly confuses students. And in fact, even in Beta's lecture yesterday, he actually mentioned that a lot of professors start by talking about black body radiation, and it doesn't serve very well. And the second reason, we just don't have time. So I'm going to skip section 3.1, but we will now discuss something called photoelectric effect, which elucidates the wave-particle duality. Okay, so so let's say that this is, I'm going to write it like this. So this is sort of subject 1, and this is 1, photoelectric effect. Okay, so what is a photoelectric effect? So this is section 3.2 of your textbook. It was known sometime before the 20th century that charged metals can be discharged with light. And it's not so surprising. Electrons are bound to the metal and require energy to be released. Light, as any wave, contains energy. And so the energy carried by light that crosses a unit surface per unit time is called intensity. And the intensity of light is proportional to the square of the amplitude. And that's what we perceive as brightness. So your eyes are intensity measurement devices. They're basically energy measurement devices. Your eyes measure average energy received per unit time, per unit area of your retina. That's what they really do. So here's what was observed. So let me describe in words, and then I will show you the simulation. First, it was found that the minimal frequency is required to get a current of electrons out of the metal. There's some kind of a threshold frequency. And light of frequency below that value, no matter how intense, no matter how bright, did not dislodge electrons from the metal. And second, for light above this frequency, did dislodge electrons from the metal, and now increasing intensity did not increase the energy of the liberated electrons, but it did increase their number. So these facts are surprising in light of the wave nature of light. So first of all, let me share the screen. I would like to show to you the simulation of this. So okay, so I'm showing the simulation. By the way, I encourage you to go and try this out for yourself. So you see right here, it says PHET, P-H-E-T. Just Google PHET simulations and then choose physics. Then go under quantum phenomena or something, quantum, and you will see this is called photoelectric effect. So let's review what I just said. If I start with a low frequency light, such as red, okay, so this is deep red, you see no matter how bright it is, no matter how intense, nothing comes out of the metal, okay? Don't mind the battery, just ignore it for now. So if let's try a different frequency of light. Let's try yellow light. Again, here I'm increasing the intensity, nothing happens. And this is strange, right? Because you're pumping more energy into the metal, so you would think that, well, something should eventually come. You're injecting a lot of energy into the metal, so sure, it should shake out some electrons. Okay, but there does exist a critical frequency when electrons start popping out. So what is that frequency? That's somewhere right here, okay? And so you can see that electrons pop out. Now, if let me choose larger frequency, yeah. So you can see that what would happen if I change intensity? You can see the speed of electrons is actually independent of intensity, but the number does, right? So with larger intensity, clearly more electrons come out. With smaller intensity, fewer electrons come out. And on the other hand, if I change the frequency, you see that the electrons that come out are fast electrons. And again, larger intensity, more electrons come out. Smaller intensity, fewer electrons come out. And so, well, how do you measure there are two things to measure. One is the number of electrons that come out. Well, you can measure the current, right? So you can put an ammeter here. And so let's do current versus light intensity. And you can see that as intensity increases, the current increases. You can put an ammeter, you can measure the current. Current is number of charges per time. So that's how you count. You don't count the electrons directly, but this is basically really, it's proportional to the counting of electrons. Okay, so you can see that as intensity changes, the current changes. What about, how do you measure the speed of electrons that come out? Well, so that's where the battery comes in. You can apply voltage in the other direction that tries to stop these electrons, right? So you see, you can try to stop these electrons. And the voltage needed to stop the electrons, to turn them around, sort of like this headwind, is larger if the kinetic energy of the electrons is larger, or if they're moving faster, right? So if they're moving faster, you see, I need to apply a larger counter voltage. That's just words. I'm not going to say any more. But my point is that using this technology, using this method, you can calculate the energy of electrons that come out. So, okay, so we can calculate the energy of electrons that come out. And so let me plot that, right? So electron energy versus the frequency. So I'm going to keep the intensity now. I'm going to change the frequency. And you can see that as frequency decreases, kinetic energy of particles decreases. And then at some point, they're hardly moving. And now we've reached the threshold frequency. If I decrease frequency any lower, nothing comes out. So you can see there exists a critical frequency, and beyond that critical frequency, electrons move faster and faster. Okay, so that's the simulation. So I'm gonna stop the sharing and we'll go back to the sketchpad. So now I've presented to you the photoelectric effect. I hope you can see me. Just a second. Yeah. So I've presented the photoelectric effect. Now let's summarize. I'm going to write something down. Here's what's observed. I'm just going to summarize. First, a minimal frequency is required to get current out of the metal. Light of frequency below a certain value, even if intense, even if it's very bright, it just simply did not dislodge electrons out of a metal, and that's hard to understand. That's not what you would expect because you are putting more energy in. Second, for light above this frequency, increasing intensity, and therefore also increasing the input energy, did not increase the energy of liberated electrons, but it did increase their number. Light. Okay, number. Pardon my bad writing. These findings are surprising if we think about, if we think of light as a wave. Well, according to the wave picture, increasing amplitude should increase the energy input into the metal, like I already said. And therefore, you would expect that it would release electrons with larger and larger kinetic energy. Second, there should not be any frequency dependence at all, because energy crossing our unit area per unit time in a light wave depends only on the amplitude but not frequency. Okay, so that's a fact that might be surprising to you. Maybe you don't believe me, but that's a result of a classical wave, because it turns out that energy density in an electric field is proportional to the square of the electric field. Energy density of a magnetic field is proportional to the square of the magnetic field. And so if a wave passes by you, what you see is you see high field, low field, high energy density, low energy density. And during one cycle, there's a certain average energy that has been delivered to you. Let's say if you're the receiver. And so the energy delivered per cycle is independent of the frequency. So therefore, over many cycles, also the energy delivered is independent of the frequency. So let me put that down. So classically, and by this I mean wave picture of light. That's what I mean by classically. Increasing the amplitude should increase the energy. You might say, well, but there's some critical energy that's required to dislodge electrons from a metal, and that's right. That critical energy is called the work function. But beyond that, if you increase the amplitude, you would expect increasing the kinetic energy. So yes, the work function might suggest that there's a critical amplitude or critical brightness, but beyond that, kinetic energy of dislodged electrons should increase. And second, okay, so second, expect no frequency dependence. Because power delivered per, no, power is energy per time, and then power per area is intensity. Power delivered per area is independent of frequency for a classical electromagnetic wave. So power is only proportional to E squared and B squared, but there's no frequency in it. That's actually an interesting fact. So the point is, something was wrong with the wave model of light. But it was already very well established that light is a wave. There was Young's double slit experiment that showed that light is a wave, and then came Maxwell's equations that explicitly explained just exactly why light is a wave or how light is a wave. It naturally showed that oscillations of electromagnetic field propagate with the speed of light, so therefore light must be a wave of electromagnetic field. So at this point, it's commonly stated that at this point Einstein proposed a particle model of light, then received the Nobel Prize for it, not for relativity, and went home. Actually, his photoelectric paper, it's not hard to find, you can find it, was which made this proposal, is actually grounded in thinking about Planck's work, which I skipped. The point is, it was built on something that Planck thought about, although Planck did suggest that black body radiation spectrum can only be understood correctly if energy of light was discretized or quantized. He did not think of this as light being composed of particles. So this is Einstein's idea. Einstein's proposal was that light acts like a particle, which are later called photons. I think maybe at that point he just called it light quanta. And photons, or the light quanta, are discrete units of light. And how does that explain the photoelectric effect? Well, Einstein proposed that the energy of this particle of light is proportional to its frequency. So you see, Einstein, he likes to sort of say, let's just start from scratch. Here's an idea, it's out of the blue, but just bear with me, that it will explain things. So we saw that with relativity, and something similar happened with a photoelectric effect. He said, well, let's just forget everything we know. Let's imagine that light consisted of particles whose energy is proportional to the frequency. And then, frequency. So then now, if frequency is too small, energy is not sufficient to dislodge an electron out of the metal, because electrons are bound to the metal. That's a normal classical idea. And a certain minimal energy is required to to dislodge or liberate electrons out of the metal. That's now called the work function. And the work function is unique to each metal. And so then any excess of energy becomes electrons' kinetic energy. And if you keep increasing frequency more, they will have more and more excess energy. And therefore, you will see that dependence of the kinetic energy of electrons upon the frequency, okay? Upon the frequency of the photons. What about increasing the intensity? Why doesn't that increase the kinetic energy of electrons. And this is really where the particle explanation comes in. Because if it is a particle, each particle carries energy. And remember, intensity is sort of energy that impacts a surface. So if light shines on a surface, intensity is really the energy that falls on that surface per time per area. But if light is made up of particles, how would you increase the energy per time per area? What do you do if you increase energy per time per area while keeping the frequency fixed? You're increasing the number of particles. So increasing the intensity, thus increasing the energy carried by light per area per time, corresponds to increasing the number of particles per area per time. Or you increase the density of photons. Okay, more photons would dislodge, so now more photons would dislodge more electrons, but their kinetic energy only depends on the frequency. So let me summarize that. So I'm going to use red color. And by the way, there's probably an interesting history involved. Einstein received Nobel Prize much later, not for relativity. I'm not sure why. Maybe people did not believe relativity. It maybe was too controversial. So in the statement of the Nobel Prize, it says that the Nobel Prize is given for his services to theoretical physics, kind of a vague term, and for photoelectric effect, for explanation of photoelectric effect. So Einstein's proposal is the following. Light consists of quanta, discrete particles. Okay. The energy of each these are called photons nowadays, we call them photons. Photon is proportional to the frequency. So the energy is proportional to the frequency, and if it's proportional, there's got to be a constant of proportionality. So that constant of proportionality is now known as Planck's constant. I will put a value later when we need it. Okay, so this is kind of a big deal, big idea. If E is less than the work function of a metal, which is energy required to liberate an electron out of a metal. Okay, sometimes we use letter phi. I think your textbook uses letter phi. So if E is less than the work function of a metal, then no electron come out. No electrons come out. Okay, because you can't there's not enough energy to pull out even a single electron. If E is bigger than the work function, right? So kinetic energy of electrons become equal to the energy of the photons minus the work function. So you put in a certain amount of energy, whatever is left after the dues are paid in order to liberate the electrons, that's what goes into kinetic energy. Okay, so this is energy of incoming photons. Okay, energy required to liberate electrons. And this is basically remaining energy. And it comes in the form of kinetic energy. And that explains that graph, right? So you can plot this kinetic energy as a function of frequency. So here is minimal frequency, HF min equals the work function. So this is then phi over h, okay? And then beyond that, you see it's linear in frequency. And so then beyond that, you just increase the kinetic energy, and we saw that in the simulation. And so moreover, increasing intensity of light. Now that if we propose that light is made up of particles, then it corresponds to increasing the number of photons that impact the metal. Now corresponds, I don't like, yeah. So more photons would dislodge more electrons, but their kinetic energy only depends on the frequency. So I want to emphasize again, what I said is first of all, it's only the tip of the iceberg. There's a lot of deep thought that went into it, in particular relating photoelectric effect to Planck's earlier proposal, the energy of light is quantized. So there's a lot going on. And what I said is a cartoonish picture with much violence to history. The point is that this effect and this explanation, why do we teach you that? Because it shows, it gives you an example of wave-particle duality. Something that was thought to be a wave, electromagnetic wave, appears to have particle-like behavior. But it's a very interesting particle-like behavior because photon still knows about its frequency. We still talk about frequency of the photon. Now, frequency is a wave idea. So on the one hand, we say, well, you can explain photoelectric effect and other things like black body radiation if we think of light as made up of particles. And then you say, wait a minute, I thought light is a wave. And you say, yeah, it still has wave aspects to it, right? There's still frequency to talk. So let that sink in, right? So this is why it's called wave-particle duality, right? Light is simultaneously a wave and a particle. And in some situations, the particle nature of light is important, like in photoelectric effect. And in other situations, somehow the fact that light is a particle is not as directly manifested, and the wave aspect of light is directly manifested. Okay, so think about that. This is an example, in an essence of wave-particle duality. Okay, so in short, things that we thought of as waves have particle-like aspects to them, in particular that their energies do not take on any values, but come in units. So this is an example of quantization. Of course, this means that there's a need for a new theory for dynamics of these phenomena. Maxwell's equations do not describe light as units. And as maybe you heard in Beta's lecture, that theory came much later with Dirac, that describes sort of quantum aspect of light. And then it was understood even deeper later by people maybe in the 50s in a theory that came to be known as quantum electrodynamics, in contrast to classical electrodynamics, which is Maxwell equation. But second, here's a thought. What do we do with experiments that, after all, showed that light behaves as a wave, like Young's double slit experiment? That was the quintessential smoking gun that shows that light behaves as a wave. So somehow we will need to reinterpret all those classic experiments that we know and love in quantum light, unintended, okay? And we will do that soon. But before we do that, I would like to describe another effect that sort of even reinforced the idea that light behaves as particles and that we really should take it seriously, and that's called Compton effect. That was also described in Beta's lecture. So in the second part of today's lecture, we'll talk about Compton effect due to Compton. Okay, so see you soon.